Now we're covering the concept of stability for control systems. And we'll start out with the concept of stability and what criteria we use to characterize a system. There's multiple definitions of stability. The one we're going to use is called bounded input, bounded output stability, BIBO stability. It means if your input is bounded and the system is stable, you're guaranteed that the output is bounded. Or if the system is stable, you're guaranteed the output is bounded if the input is bounded. So that's what we'll use. Bounded, by the way, is a characteristic of a signal. Stability is a characteristic of the system. Here's the output in the Laplace domain. The output is the product of the transfer function, the system, and the input. Signals are the R and the Y, the input and the output. The transfer function is the system. The system converts an input to an output. Boundedness is an attribute of the R and or the Y. But this transfer function in general would look like this: a polynomial in S over a polynomial in S. And we'll say the input has the same form. After any zeros cancel any poles on either side, and you do partial fraction expansion, it becomes a sum of terms like this, where these lambdas are the poles, or the combined poles of both of these after cancellation. The mu's is how many times any given pole is repeated. And then when you inverse Laplace transform that, you get the output, which is a linear combination of these mode functions. And these are what the mode functions look like. Lambda could be complex, in which case this exponential term is oscillation or a sinusoid in an exponential envelope. Whether that envelope is growing or shrinking depends on whether the real part of that pole is positive or negative. If the real part of that pole is strictly negative, this whole mode function is going to shrink to zero. We're going to look at these limits as time t goes to infinity to see if this thing stays bounded. If t goes to infinity. So that's the easy case. When the real part is strictly negative, it's going to shrink to zero. Oh, that's because by L'Hopital's rule, the exponential wins over this polynomial and it shrinks to zero. If the real part of this guy is strictly, if this pole is strictly equal to zero, or exactly equal to zero, this is a constant or a constant sinusoid, a sinusoid of constant amplitude. And if this alpha equals zero, this is a constant, so it stays bounded. It's just one or a sinusoid with a amplitude of one. If the real part of this pole is greater than zero, or it equals to zero, but alpha is greater than zero, meaning that pole is repeated, this thing will grow off to infinity. That is unbounded. The troublesome case, the easy case, is if all poles of both the input, well, first notice that the poles of the output are a combination of poles of the input and the transfer function. If all poles of both these guys are strictly in the left half plane, the output's going to be bounded. That's the easy case. The sort of troublesome case is when the rightmost poles are on the imaginary axis. Any signal is going to be bounded if all its poles are strictly in the left half. And it'll be unbounded if any pole is in the right half plane. particularly in the right half. If its rightmost poles are on the imaginary axis, it'll be bounded if it's simple, bounded in the sense that it's just a constant or constant amplitude sinusoid. But if that pole is on the imaginary axis and repeated, if any such pole exists, then that signal is unbounded. We can go through some of the logic. I'm not going to go through all this. I'm just going to summarize how we're going to characterize it, the easy way to characterize a system. If all poles of the transfer function are strictly in the left half plane, you're guaranteed the output will be bounded if the input is bounded. We call that stable. If any pole of the transfer function is in the right half plane, or its rightmost pole or poles are on the imaginary axis but repeated, then it's unstable. If the rightmost poles of the transfer function are exactly on the imaginary axis and they're simple, meaning not repeated, we call that marginally stable. What happens in that marginally stable case is that for most inputs, the output will be bounded, but there's a certain input, an input that has the same frequency or the same pole as your system pole, then you'll get an unbounded output due to that input. Anyway, recall this picture. Strictly in the left half plane, you get shrinking envelopes. Everything's nice and bounded. Strictly in the right half plane, you get growing envelopes. They're unbounded. If they're exactly on the imaginary axis and simple, you get either a constant or a constant sinusoid. But if it's repeated, these envelopes will grow according to the power of t, how often it's repeated. It'll be polynomial growth, not exponential growth. So stability is an attribute of the system, not the output. It's a system attribute. You learn it or determine it from the transfer function. And note, if you say something is not stable, that doesn't mean it's unstable. It could be marginally stable or unstable. And it's all based on the pole locations of the transfer function. Zeros have nothing to do with it. I'll go through some examples next time. So that just kind of explains the concept and how we came up with the criteria.